So this video we're looking at simple harmonic motion again. We're looking at the example of a mass on a spring. We've got simple situation, complex situations, and variation, which is basically the same, but it uses a different setup, which appears to be so. So first of all, a mass on a spring, there's two ways you can look at it. You can look at it sideways, which seems to be mentally better. You've got a spring fixed to like a wall. This could be a wall. This is our spring. And we've got our mass, and presumably there's some sort of frictionless surface, like an air table, so frictionless surface upon which it can slide, so mass will slide back and forward along there. You would just grab the mass here and pull it back and then release, or you would compress it and then release, and it would just start oscillating back and forward according to simple harmonic motion. It's simple harmonic motion because remember, with simple harmonic motion the definition is that the force, the restoring force, is proportional to the displacement, or negative displacement, so that the further out you go, the greater the force pulling it back to the centre is. So that's a mass on a spring. And some variations, or some complex variations of that, could be, let's just move this a little bit, could be a system like this, where you've, okay, so I just had a little interruption. So we're doing a complex variation where you could have a spring with a mass and then another spring attached to the wall like this. Okay, so between two fixed surfaces where the mass oscillates back and forth. Your spring constant in this case, I haven't done the formula for this, but your spring constant for the spring is just going to be twice the spring constant, assuming that it is the same k, so it would be k times 2 would be the spring constant. Now I should have gone up and given you the formula, so we'll drop back and we'll do that. The formula for a mass on a spring for the period is going to look very similar to the pendulum, m over k. Okay, so in the pendulum formula it was t equals 2 pi square root L upon g. This time it's t equals 2 pi square root m upon k. So that's a nice little parallel there. Don't be misled into thinking that the square root is always going to be appearing in a simple harmonic motion equation and with the 2 pi and that. It just happens to work out in this case nicely, because we have the, well, it may appear, but it seems, when we derive it, we come up with the angular velocity, or the angular frequency of the reference circle, and then that happens to be an omega squared thing because it comes from the acceleration being omega squared y, and then that you have the square root of the part that equals to omega. Anyway, we want to carry on. Let's do a few more variations. Pretty much you can have different variations as combinations of springs. You could have a double spring system like so. Now, what did I said? The spring constant. Yeah, anyway, you could have a double spring system like this. And this case, where it's oscillating backwards and forward, in this case it's also, the spring constant is going to be times by 2, because you have to pull twice as hard. If that's assuming they're both k, you have to pull twice as hard to get the same extension out of the spring. You're working against both springs. So these two examples here, this one and this one, they're both ways where the spring constant will be added. This one here, this is interesting, because if you added the spring in a different way, it might not do that. Okay, so if you doubled the length of the spring, that's actually going to make it floppier. Okay, so let's draw that as an example. If you just had, oops, that's what I'm trying to draw. Spring like this, plus a spring like this, and then a mass, that's actually going to be floppier than the original one. So this is k, and it's actually going to extend easier, so you're going to divide the spring constant by 2. Whereas in the example above, we found that we're having to work against both of them when we're moving this. That's why the spring constant adds. rather than divides, or multiplies rather than divides. Okay, so let's go to yet another example, and this one could be the confusing one. I think I spoke about this in an earlier video, but we'll mention it again anyway. This is a vertical arrangement with your spring and your mass, and it's going to oscillate up and down. Now it seems like the reason I've highlighted this as an example is it seems like it's going to be difficult to work out because the forces are going to be tricky, because you also have to include the force due to gravity. And how does that affect it? Well, the answer to that is that it doesn't, because you can just let the mass sit and it'll find its own equilibrium level. And then we can completely ignore gravity because the forces are balanced at that equilibrium position. And then when it moves vertically away, it'll have a force proportional to the displacement. So nice, easy, no problems. You can forget about it. Okay. Last, now the more complex variation that I wanted to give you, which is still essentially a mass on a spring, is something called a loaded vibrating blade. So we've got a like a metal ruler or piece of metal that's flat, and you stick your mass on the end, and then you flick it and it'll vibrate up and down. So this is clamped in place here, so that's, we'll call that a clamp or something. Clap, you can clap if you like, but clamp. So it's going to vibrate up and down when you give it a flick. You've done this with a ruler and you make interesting sounds with your ruler, but in this case we're vibrating it up and down. The period is still equal to 2 pi times the square root of m over k, and you adjust this mass to change that. So when there's no mass, it's going to vibrate really fast. When there's a lot of mass, it'll vibrate slow. Video's gone too long. That's enough for now. That's a lot of springs and spring variations of simple harmonic motion.